Hi, I'm Sam Leeman-Munk, affiliated with North Carolina State University in SAS. I'd like to present deep encoding and reconstruction of normalization for noisy text. So noisy text is important because it's all over the web. There's so much of it, but it's problematic to access because most text analytics techniques are based on normal text. So the obvious solution is to take noisy text and convert it into normal text. And that's what the competition was about. So my approach to this competition was to see how far I could get using just deep learning, helping deep learning as little as I could. And so my system uses no hand-engineered features whatsoever. And it also uses no external data or off-the-shelf tools. And as a consequence of this, without these and unlimited data, it was not able to take advantage of context, so it also does not use context. So the inspiration for my system was denoising autoencoders. What are denoising autoencoders? Well, let me start by describing what autoencoders are. So with autoencoders, your goal is to take an input and encode it such that you can output the same thing that you input. Reconstruct the input is the term. So denoising autoencoders add noise to their input and then try to predict the original input without noise. And they denoise it. So the application to noisy text normalization should be obvious. So my model is basically a feed-forward neural network with a projection layer and a multi-softmax layer. So I'm going to talk about these one at a time. First, let me start with the projection layer. So the projection layer takes a table of all the letters in the alphabet. So each time it finds a U, it takes the weights that are associated with that U. In this example, we have 3 weights associated with U, and it sends those as inputs. And there's also a blank character. And this blank character is padding for when we don't have enough letters in the word to fill up the whole window, which is most of the time, because we have a window system since we always have to have the same number of inputs to a neural network. So you can think of these weights for each letter as a point in multidimensional space. And we can flatten those points in multidimensional space to show relationships between the letters. And at first, since they've been initialized randomly, these weights, the letters have no relationship to each other. All the characters are just randomly displayed. Whereas after 60 training iterations, we see a lot more order. For example, you can see that the green hashtags and punctuation are sort of separated from everything else. And so what we see here is that we can learn meaningful information that humans can understand automatically, directly from the data. Meanwhile, the hidden layers, these are just feed-forward layers, and their job is to interpret the information that's coming from the projection layer and get a sense of what is the word that we're looking at, so that we can then send that information to the multi-softmax layer, which will regenerate the word. And the multi-softmax layer regenerates the word by making a probability prediction for each position in the window. So at position 1, there's a probability that the letter Z is going to show up. And the probability the letter A is going to show up. And the same thing for every letter in the alphabet. And the most likely letter is Y in this case. And same for the second position, the most likely letter is O. Third position, the most likely letter is U. And so we take all the most likely letters and we get YOU. And so this model looks pretty good. So how well does it work? So when we are looking at this graph, one thing we should note is that this is the percent error, so lower is better. And of course, the longer we train it, the better we do. But 24% is the lowest error that we were able to get using only the normalizer as I just presented it. So in order to improve that, we've added 2 extra modules. We make this whole pipeline, so to speak. And it starts with the letter U as the input. And so then this goes to pre-processing, which pads it so that it will fit into the normalizer and flagger properly. And so then it sends it to the normalizer and the flagger. So I've mentioned what the normalizer does. Let me say what the flagger does. The flagger decides whether it should be normalized or not. So it flags it as do normalize or do not normalize. Meanwhile, the normalizer guesses a normalization and then sends that to the conformer. I'll talk more about this pretty soon. But the conformer, its job is to take the word that the normalizer has predicted and just fix any little errors by pointing it to the closest word in the vocabulary. And I'll say that in more detail soon. So then we either output the original input if we didn't need to normalize, or we output the normalized conformed version. So let me talk about the flagger. The flagger is pretty straightforward. It's the same structure as the normalizer, except it's just predicting whether to normalize or not to normalize. Meanwhile, the conformer is based off the observation that the normalizer is prone to minor errors. So, for example, there's a particular configuration of lol that will lead the normalizer to predict laggling out loud instead of laughing out loud. We predict that this has to do with a limited amount of training data can lead to these sort of weird little quirks. Similarly, bomb gets corrected to bomu instead of bomb, and LMFAO gets corrected to 27 characters, the correct correction, but we use a 25 character window and it doesn't fit. So the conformer simply takes the word and uses a Levenshtein distance to pick the nearest known vocabulary word that it selects from the training data's correct answers. So it can correct laggling out loud to laughing out loud and bomu to bomb, etc. And it can also extend things that don't fit in the window. So our final model settings use 25-dimensional character projections, and the flagger uses 2 hidden layers of 1,000 nodes each, and the normalizer uses 2 hidden layers of 2,000 nodes each. And with these settings, our model performs quite respectably. It gets 90% accuracy and 74% recall and 81.5% F1 score. And let me reiterate that we achieve this score with no feature engineering, no external data or off-the-shelf tools, and no context whatsoever. So, in conclusion, the direct application of simple deep learning techniques without feature engineering is effective for text normalization. And a text normalization model can be effective even when trained without context and unlimited data. So for our future work, we are thinking of simplifying the normalization pipeline to see if we can, just using the original normalizer, get the kind of results that we were getting with our whole pipeline, or even better. And to do that, we might use external data. One thing we could use external data for is to get lots and lots of information about the typical formation of language. And so that would help us to deal with these sort of off-by-one errors, at least, because we would find out that words like bamu don't really appear nearly as often as words like bomb. And we could also investigate other sources of noise, such as the noise generated by novice writers in 5th grade science text, for example. Finally, we'd investigate the overall utility of normalization, because it's very possible that many tasks might be well served by just taking unnormal data and making it to normal data. Some tasks might lose out on that. For example, sentiment might lose out if we forget that COOL had all those extra O's and just normalize it to cool, because we lose some emphasis. So I'd like to thank my collaborators at North Carolina State University and SAS, and thank you all for listening.